talk is well, I'll have some distracting things to say too, but yeah, this is, as you can see, this is joint work with my father. But I also have some other joint work to present, so I will move on. This joint work is with my colleagues from Loyola, Bob Jensen and Nick Barron, and the subtitle could be a PDE excuse to have some fun basic convex analysis. I hope that at least you appreciate the pictures. Also, I have to say, like, I feel a little bit suspicious about the camera out there because, like, I have to be careful what I say because then, you know, whatever I say can show up on the internet later. Okay. Don't stress me out even more. Thank you. Okay. What is a quasi-convex function? At least one way to understand it, or call it differently, would be a sub-level convex function. It is a function whose sub-level sets are convex. In most of the talk, I will allow plus or minus infinity as values, but interesting things show up even if you don't. You can do a global definition or a definition of a level convex function on a convex set. Some examples, of course, every convex function is quasi-convex. Arctangent is a very nice example of a quasi-convex function that's not convex. Natural log extended by minus infinity to non-positive numbers is a perfectly good quasi-convex function. And the two examples I just mentioned don't behave very well under linear perturbations. We know that you take a convex function, you add another convex function, so in particular a linear one, you still have something linear. And this really corresponds to taking the graph and trying to tilt it to one side or the other a little bit. For quasi-convex functions, things go very bad. Right, you tilt arctangent a little bit, you push the right end of the arctangent down, you end up with something that does not have convex level sets anymore. There has been a lot of work on quasi-convex functions, including first order conditions, properties about the subdifferential, etc., etc., a couple of different duality theories. The only thing I want to mention, because I will generalize it in a moment, is a second order condition for a smooth function to be quasi-convex. There is a necessary and sufficient condition. Necessary condition for quasi-convexity is that if you look at the Hessian in the directions which are perpendicular to the gradient, the Hessian is positive definite. And a sufficient condition is if you look at the directions perpendicular to the gradient and the Hessian is positive definite, you have a quasi-convex function. And minus x to the fourth is a perfect example how this necessary condition fails to be sufficient. So in other words, yeah, for this function right here, the gradient is 0 only at 0, or the derivative is 0 at 0, and the second derivative is also 0. So generally this holds, but the function is spectacularly not level convex. How to generalize this second order condition in general, since I'm working with two colleagues who work in PDE theory, we looked at viscosity descriptions. What do I mean by that? Instead of looking at a function, we'll look at smooth functions that touch a function from above. So before I get to talk about the technical details, look, I mean, there is a picture. I'm touching the blue function by smooth functions from above. This function touches where it's pretty much horizontal. So let's say the gradient of the green function is 0, and the second derivative is positive, so all is good. This function is, well, the second derivative is positive, definite. This function looks like I'm touching above with a green function, and it looks like it's concave, so the Hessian is negative definite. But that's fine, because I'm touching at a point where the first derivative is not 0. So in other words, these three green functions touching from above seem to be okay with level convexity. The problem is right here. I'm touching with a function that's certainly negative definite, or the Hessian is negative definite, but the first derivative is 0. And touching above by something like this is definitely a problem for quasi-convexity. So now to introduce some technical terminology, we have this, look at the operator, which is, think of this as a function of a gradient and of the Hessian. We're looking at the directions which are perpendicular to the gradient, and we normalize everything, and we're looking at the quadratic form of the Hessian. And the function f is a subsolution of this inequality if this inequality holds for every smooth function touching f from above. And maybe not very surprisingly, the second order characterization of quasi-convex functions carries over if you drop any assumption about smoothness. I mean, you can have minus infinity as a value here as well too. All you need is upper semi-continuity. And I already feel a little bit suspicious talking about upper semi-continuity here, where we want functions to be lower semi-continuous. But I said things are interesting enough if you think about continuous functions only. So, in terms of viscosity subsolutions, quasi-convexity of f means that f is a subsolution of this operator. If f is a subsolution of the strict inequality, then f is quasi-convex. So this is essentially a direct translation of the first two smooth conditions. And finally, if you have a subsolution of the non-strict inequality, and your function doesn't have any local minima, doesn't have any local maxima, you're okay. You get quasi-convexity as well. And here is an example of a function which actually has a local maximum. This function is x minus 1 to the fourth minus 1 here, and then it's reflected symmetrically here. It has a local maximum. It satisfies this inequality even in the smooth sense, and it's not quasi-convex. Okay. And the real topic of my talk is what happens if you study this operator L0, or you study the differential equation involving L0, and you decide that it's really not very good. There are some bad things about this operator. You want to introduce something that's a little bit more regular, maybe even without any convex analysis in mind, but something interesting from the convex analysis side comes out. So here is some, again, viscosity theory PDE motivation for what I'm about to do. I'm going to say a few words about viscosity solutions of equation of PDEs like this. What is a viscosity solution? Well, it is a subsolution in the sense I just defined, and also a super solution in the sense that you're touching from below, and you want the inequality here going the other way. Equations PDEs like this, of course, plus some boundary conditions. You want to ask questions about uniqueness of solutions, again, in general, non-smooth solutions, not necessarily continuous even. Everything goes good if this function g, if the right-hand side is bounded below by a positive constant. And the good thing is, if you look only at quasi-convex solutions, you actually do have uniqueness. And I appreciate I'm skipping some technical details here, what assumptions you actually need, but essentially this is the big picture. If you look at a regularized version of this L0, I'm going to specify this in a moment, essentially, looking ahead, you want to look not just at the directions perpendicular to the gradient, but you want to look at the directions that are more or less perpendicular to the gradient. Again, details are coming up. If you look at PDEs like this, non-negativity, so you don't need to have G strictly positive. Non-negative is okay. You get uniqueness of solutions. And solutions to this guy approximate the unique quasi-convex solution to this guy as you let epsilon go to 0. Well, and there are some other PDE reasons that I am not able to repeat even that suggest that equations like this behave better than this one. It turns out that descriptions like this L epsilon, or the particular generalization of quasi-convex functions, was studied before. The only papers we managed to find it was by Fu and An, and then An later. They called them S quasi-convex or stable quasi-convex. I unfortunately decided to try to change the terminology because Stable quasi-convex didn't sound good, and it seemed like it should be stably quasi-convex, and I don't think stably is even a word. So we started using the terminology functions which are robustly quasi-convex. So a function is epsilon robustly quasi-convex if you can perturb it by linear functions with slopes less or equal than epsilon, and the quasi-convexity is preserved. Here? Oh, yeah, certainly. Thank you. Yeah, this should be quasi-convex. I gave a similar talk at the PDE conference very recently, and I was very glad that the projector was much lower, because I could stand in front of the screen whenever there was a typo. And I was very, yeah, my shirt had enough stripes on it that it was absolutely unreadable. Okay, so yes, a function is robustly quasi-convex, or epsilon robustly quasi-convex if you can perturb it by small affine or small linear perturbations and you preserve quasi-convexity. And for short, I'll just say robustly quasi-convex if it is epsilon robustly quasi-convex for some epsilon. Examples: every convex function is robustly quasi-convex for every epsilon, in fact. And in fact, the converse is true as well. So a quasi-convex function that you can perturbed by arbitrarily big linear functions and preserve quasi-convexity is convex to start with. Natural log function, even when we look at positive reals, it's quasi-convex, it's pseudo-convex. Pseudo-convexity means essentially, or one way to think about it is that the steepest descent works, or the other is to say that pseudo-convexity means if you have two function values and function is smaller here than here, then the directional derivative of this point facing this way will be negative. But this function, natural log, is not robustly quasi-convex. Again, you can push the natural logarithm down a little bit and lose convexity of the sublevel sets. A robustly quasi-convex function happens to be pseudo-convex, but again, the reverse doesn't work, and the reverse doesn't work not necessarily for global reasons. In other words, you don't need to look at natural log of x and look at behavior at infinity. You can actually construct examples which quasi-convexity, robust quasi-convexity fails locally at a minimum, but pseudo-convexity is perfect, stays in place. Okay. First, going back to Ann 06, necessary and sufficient condition for epsilon quasi-convexity is this. You look at all the directions perpendicular and not quite perpendicular to the gradient. And in these directions, you want the Hessian to be positive semi-definite. That's necessary and sufficient. Nice byproduct of this is if you have a differentiable robustly quasi-convex function, then it's actually convex around its minimum. And the reason is if you have, at a minimum, a convex function has a zero gradient, and nearby the gradient is almost zero. So this is not a constraint. So this has to hold. So you really get convexity around the set of minimizers. But again, for non-smooth functions, that's totally false. You can probably expect I'm about to present a viscosity version of this. So here we're looking at this more regular operator L epsilon. We're looking again at directions that are within epsilon of being perpendicular to the gradient. If a function is a subsolution of this inequality, then it is epsilon quasi-convex and vice versa. Now, I should probably try to prove something, so I'm going to very quickly try to tell you where this is coming from. In this result, first, proving that epsilon quasi-convexity implies this is essentially a second-order expansion, and it's simple. Proving sufficiency of this condition, there's different ways to do it. One way involves a pretty simple variational argument, so this is a good place to present this. Let's say we have a function that's not epsilon quasi-convex, which means we can perturb it in a certain direction by a small linear function and get something that's not quasi-convex. So I'm assuming that this f sub v, where f sub v is here, is not quasi-convex, which really means that you can look at along a certain segment, and the maximum of the function along this segment is attained in the interior of the segment. So let's say somewhere here. Without loss of generality, I can change coordinates and say that something happens between 0 and 1, and this is my x1 direction, and these are all other variables. I have along this segment quasi-convexity of f sub v fails. In other words, the maximum of f sub v on this segment is somewhere here. I'm going to look at test function like this. First, immediately I will let I go to infinity. And what do I get? Well, when I goes to infinity, this converges epigraphically to the indicator of the horizontal axis. Which means if you look at this limiting function phi, let's say phi infinity minus this f, you really look and you're trying to minimize it, you are really maximizing this function f sub v along a segment. We know that the maximum is attained somewhere on the interior. And then the epi-convergence theory says that for I big enough, phi I minus f sub v attains a minimum somewhere here. Or maybe here. Okay. What does that mean? Well, then you look at this function. Phi I minus f sub v having a minimum really means that you're touching the function f v with a phi I from above. Phi I is smooth. You check the L epsilon operator for this function, and it's negative. And there's your contradiction. I can also very quickly tell you that I did state earlier that if a function does not have a local maximum, and it is a subsolution of this inequality with L0, then the function is quasi-convex. How do you prove it? The whole story is similar, only you have to be more clever about your test functions. You use test functions with sub-level sets that look like this. And what you use this assumption about f not having a local maximum, you use it to touch with a test function like this, but not along the x1 axis, but somewhere here. And then you evaluate L0 at a point which is off the horizontal axis, you end up with something negative. Okay. And this is it for PDEs. What can I tell you about those epsilon quasi-convex functions sort of from the basic convex analysis part? So this is where I stand in front of the projector and like obscure what I wrote here, because this shouldn't be here. But first about the picture. If you have a stationary point of a robustly quasi-convex function, that's very easy to see, even in a generalized sense, then it has to be a global minimizer, because if it's not, you can tilt it, and quasi-convexity will be ruined. So there is a stationary point in the generalized sense right there. You tilt it a little bit up, so you push this thing up. This is the picture you get. This is not quasi-convex anymore. Since I have the blackboard, what I really should write on the right-hand side is the bottom inequality. If f of y is less than f of x, then the directional derivative of f in the direction of y from x is really bounded above by minus, and then you have a minimum of epsilon y minus x, but also f of x minus f of y. So again, this purple thing right here should replace this. I briefly mentioned what a pseudo-convex function is. A pseudo-convex function is a function which would have satisfy this with 0 right here. What I wrote here suggests that these robustly quasi-convex functions are pseudo-convex in some particular strong sense, but it's different from all the strong senses of pseudo-convexity I managed to find. Okay. Some more, I think, interesting convex analytic properties if you look at the sub-level sets of a robustly quasi-convex function, and you look at their recession cones, all these recession cones are the same, as long as you look at non-empty sub-level sets. What is a recession cone? Right, it is a cone of all directions in which you can move in a convex set. So we're looking at sub-level sets for two different R's. The recession cones, robust quasi-convexity, suggests that these are the same sets. Well, where is it coming from? If you pick R1 less than R2, then one inclusion between sub-level sets is obvious, because the lower level set is smaller than the bigger, so recession cone is smaller than the one for the bigger. How do you prove there is verse inequality? Well, if you have a direction in which one sub-level set goes forever, but the other one doesn't, then you just take this direction and push it down a little, and you'll end up destroying quasi-convexity. A particular consequence of this is that robustly quasi-convex functions that are bounded above are constant. Both of these properties sound very much like convex functions. But some other properties suggest that, well, okay, maybe they are close to convex, but they're also not. Parametric optimization using robustly quasi-convex functions preserves robust quasi-convexity, only maybe the epsilon changes a little. Composing a robustly quasi-convex function with a affine function is fine as long as you have an invertible matrix, which is really different from convex functions, which you can compose with any linear function. And I think one way to think about it is that this non-invertible matrices ruin some of the strictness. And to see that you can't do really much better, I can tell you another property. If you have a function that's robustly quasi-convex as a function of two variables, x and y, but it really depends on x only, but again, x's and y's can be here of arbitrary dimension, as long as it's finite. Actually, it doesn't matter if it's finite, but anyway. If you have such a function, and it depends on one variable only, it actually has to be convex in the first place. The picture suggests how would you prove it. We have a function of x and y. It really depends on x only, and we are assuming, let's say, by contradiction, that along this segment, let's say the function is not convex. Well, what does that mean? That means you can find 3 points, this point and this point, and the point somewhere in the middle, in between them, where the usual convex inequality fails. What do you do then? Well, you start going uphill a little bit this way, you start downhill a little bit this way, until the value of your function, going up and down a little, here and here is the same, and here it's actually more, which contradicts quasi-convexity. It's really basic argument using convex inequality for nothing else. You can prove it if you want the second order necessary subdivision as well. So this holds out on the property of the Hessian. In fact, if you have a robust quasi-convex function which is constant along a segment, which is a much weaker assumption than what I had here, that every point of that segment, the Hessian is positive, semi-definite. And that's really playing with the Hessian. Okay. After mentioning several properties, after actually discovering some of them, I was facing the problem like, okay, where are these functions coming from? Convex functions, of course, satisfy all this, but are there any other ones besides one-dimensional ones? The papers by Fu and An we found before had some examples, but they were strangely one-dimensional only. You can actually produce interesting examples using the second-order conditions. Here is one, and rather than reading all the details, again, I would rather have you look at the picture. First class of robustly quasi-convex functions comes from rotating functions of one dimension. So here, let me sketch a couple of different functions that you can rotate and get something robustly quasi-convex. Let's see, you can take something like this, and they don't necessarily have to be continuous. You can do something like this. You can start with a function that's minus infinity and does something like that. can take something like this. The precise conditions that you need are really captured here. But I think visually everything I sketched would be okay. You rotate these functions around the vertical axis, you get something robustly quasi-convex. And certainly you can get functions that are not convex this way. Another thing you can do, you can start with a strongly convex function. What is that? It is a function from which you can subtract a multiple of a quadratic or of the norm squared and still be convex. Start with a strongly convex function. You take its natural log. Well, and if you really want to take logs of non-positive numbers, then you just put them as minus infinity. You get something like this. On every set, on every convex set on which G is bounded above, you end up with a robustly quasi-convex function. So there's another family of examples. And I think I have like a minute and a half. So I don't have pictures for this, but so very recently I looked at problem, I think that goes back to Fenchel, of when can you take a nested family of convex sets and arrange them in such a way that they build a epigraph of a convex function. To say it differently, when can you take a quasi-convex function and you can compose it with a increasing function of the reals to produce a convex function? And there are various conditions that guarantee this. Robust quasi-convexity seems to give you a very, very simple, sufficient conditions for this. If you take a robustly quasi-convex function whose Hessian is bounded below uniformly, you can actually take the exponential function of that, maybe with a big enough parameter. So instead of you look at e to the kf with big enough k, you end up with a convex function. And you don't need any other conditions, which are sometimes pretty technical and are featured in other approaches to this problem. And this would be about it. Some self-advertising, and I wanted to thank NSF and thank you for your attention. Actually, and before, one more thing. I really think that there's enough cute little things you can say about epsilon robustly quasi-convex functions that there should be some information on them somewhere. Nobody in the PDE audience last week could suggest anything except Bob Jensen, who's working on this with me. But yeah, if you have any even clues or hints where to look, I'd appreciate this. All right, thank you.
Raf, does anybody have any questions or care to give Raf a clue?
Yeah.
Sorry, you're going to have to remain clueless. I had to set it up. Quick question. It seems to me that robustly quasi-convex functions might provide a class of non-convex functions where you can prove strong convergence results for algorithms. Have you looked into that at all?
No, not yet. Well, okay. I looked at in the most basic sense. Steepest descent here works like a charm. And one reason is that as long as you know that your argmin is bounded, you have inf compactness of your function. That's one reason. And also you don't have any flat spots, and you have, I think, based on the inequality that was here, you can probably work something out. So yeah, this wouldn't surprise me, but my fear is that pseudo-convex functions probably were looked at exactly for this purpose, and some variation of pseudo-convex function out there, somewhere that I don't know where to look, might have addressed this.
Patrick?
Yeah, I forgot the name he gave to them, but I think Didier Ossel studied also functions that were quasi-convex and never flat except at the global minimizers.
Except at the minimizers. Well, I mean, pseudo-convexity, I think that's actually equivalent. A quasi-convex function which doesn't have any flat spots except at the bottom is pseudo-convex.
Yeah, but there was something else because the Ozookian subdifferential had nice properties in that sense. Yeah, I mean, there are many variants, but anyway, and in the applications for, let's say, procs, essentially with such function, procs behaves nicely almost as though you had, convex function, at least in 5 dimensions. So they are, for algorithms, those are very useful functions also. But you may want to check the details. I think he had many classes like this, and one of them may be related to your robustly quasi-convex class also.
Any final comments?
Rafal, you did a lot of applications, as far as I know. Could you present and mention maybe the most striking application where quasi-convexity plays a role, but convexity does not?
Okay, L-infinity calculus of variations, for example.
For what? For existence?
Well, for relaxation, right? We know that we really like, in standard calculus of variations, we like convex functionals in the velocity variable. In L-infinity control, you want to quasi-convexify them. That's one.
Well, I think it was some work of Nick Barron about this L-infinity. You mean this one, right?
Among others, yes.
I see. It means we don't have relaxation via convexity as usual.
Correct.
Oh, that's interesting.
Some other cases, the PDEs like this actually show up in characterizations of various games, like tug-of-war games where one player moves, or you flip a coin and one player can move a certain distance or the other one, and so on. So, yes, I'm not extremely prepared at the moment to mention all the details, but these are applications in which it's not quasi-convexity shows up naturally, but some PDEs describe what's going on. And if you look at the PDEs deep enough, you'll see that part of the PDEs guarantees that you actually are getting quasi-convex functions.
Thank you.
Sorry, Terry. In order to let people get their coffee, we do start again at 4 o'clock, so I think we'll take off now, and Terry, you'll just have to ask Raf privately. Sorry.